Now, how do we find the length of this line? By measuring it. And remember, measurement is comparison. To find the length of a line, we usually pick a scale or ruler and place it next to the line with one end of the line coinciding with the first marking on the scale, and take the reading on the scale at the other end of the line as the length of the line. That is how we generally do it. And on this scale, each division is 1 centimeter long. So by looking at this picture, we would think that the length of the line is between 3 and 4 centimeters, because this end of the line falls between two markings numbered 3 and 4. So it is 3 dot something centimeters. But if you observed this scale carefully, you would understand that this measurement is wrong, because the numbering on the scale must start with a 0, but it has started with a 1. So the actual length of the line is between 2 and 3 centimeters, or it is 2 dot something centimeters. So because of this wrong numbering on this scale, the measurement we obtained is wrong or erroneous. Such errors are known as systematic errors. Errors in measurement that are produced by defects in the measuring device. Not only this measurement, every measurement we make using this scale will be erroneous. Not only they are all erroneous, but they are all bigger than their actual values. See, in this case, if the actual length is between 2 and 3 centimeters, the measurement we obtained says that its length is between 3 and 4 centimeters. It is bigger than the actual value. So, every length measured using this scale will be bigger than its actual value. So if we plot them on a number line, they would all fall to the right of their actual values. That is why we call them unidirectional. So systematic errors are unidirectional. And the interesting thing with systematic errors is they can be corrected. The moment we notice this error, we can apply a correction to each of these wrong measurements to obtain their actual values. So, systematic errors can be corrected. And here we have another defective scale. The numbering looks fine, but each division on this scale is longer than 1 centimeter. Though the scale says each division is 1 centimeter long. The length of the same line measured using this scale would be 1 dot something centimeters, because this end of the line falls between these two markings. Obviously, this measurement is also wrong. The actual length of the line is somewhere between 2 and 3 centimeters. And this error in measurement is also caused by a defect in the measuring device. So this is also a systematic error. But in this case, the measured length is smaller than the actual length of the line. And every length we measure using this scale will be smaller than its true value. So they would all fall to the left of their actual values. So these are also unidirectional. And they can also be corrected. Once we know the actual length of each division, we can apply a correction to each of these measurements to obtain their actual values. So what are systematic errors? They are errors in measurement that are caused by defects in the measuring device, and they are unidirectional and they can be corrected. Say finally I found a scale that is free from all defects, and when I measured the length of the same line using this scale, I found its length to be 3 dot something centimeters, because to me this number appeared like a 3. And obviously this measurement is also wrong. But this error in measurement is not because of a defect in the scale. The scale is fine. But this is caused by a defect in my vision. I have a defective vision and I am not wearing my eyeglasses. So all these numbers are blurred. Therefore, I made a wrong measurement here. Such errors are known as human errors. And strictly speaking, these are not errors, these are mistakes. Unlike systematic errors, human errors can also be eliminated. In this case, to eliminate human errors, all I have to do is wear my eyeglasses. Now I am wearing my glasses and picked a good scale. So both human errors and systematic errors are eliminated. And on this scale, each division is 1 centimeter long. And by looking at this picture, we understand that the length of the line is between 2 and 3 centimeters, or it is 2 dot something centimeters. Because this line completely covered 2 divisions and projected slightly into the 3rd division. And if this is the measurement we obtained, then what do we understand from this measurement? All we can tell is that the actual length of the line is somewhere between 2 centimeters and 3 centimeters. But we do not know the exact or the true length of the line. So this measurement gave us a range within which the actual length of the line would fall. So there is some uncertainty in this measurement, because the true length of the line could be anywhere between these two values according to this measurement. And we cannot tell where it would fall. And this range is what we call the range of uncertainty. And the reason we are unable to tell the exact length of the line from this measurement is because we do not know the value of this something, right? See, we were able to read the value of this digit directly from the scale by using the divisions present on this scale. But there are no smaller divisions on this scale to read the value of this something straight out of the scale. Now the question is, if you cannot read the value of this something out of the scale, can you at least estimate or guess its value? I think we can do that. Now, to measure the length of any line, we have to take 2 readings. One reading for each end of the line. Let us call the reading at this end of the line RA and the reading at this end of the line RB. Then to get the length of the line, we have to subtract RA from RB. Now what is the value of RB? Now looking at this picture, we can tell that it is 5 dot something. It clearly crossed the marking numbered 5. Now can we estimate or guess the value of this something? I think we can. In our mind, we can imagine that this division is divided into 10 equal divisions and use these imaginary smaller divisions to estimate the length of this portion of the line or the value of this something. Now, the smallest division physically present on this scale is 1 centimeter long, and the smallest division on any measuring device is called its least count. The least count of this scale is 1 centimeter. Now, we are imagining that this division is divided into 10 equal divisions. Then what will be the size of each of these smaller imaginary division? It would be 1 centimeter over 10 or 0.1 centimeter or 1 millimeter. Now, according to me, this portion of the line completely covers two of the smaller divisions, and the size of each of the smaller divisions is 0.1 centimeters. So, in my honest opinion, the value of something is 0.2 centimeters or RB is 5.2 centimeters. So now in this reading there are two digits. The first digit is obtained by using the markings physically present on the scale. The second digit is obtained by using our imagination. We estimated its value. Remember, these divisions are not physically present on the scale. They are only in our imagination. Now, if you ask me how confident are you that the value of RB is 5.2 centimeters? See, I am very confident or 100% confident about this digit, but I am not so sure about this digit because the value of this digit is estimated using my imagination. And my imagination need not be 100% accurate. So if someone else takes the reading of this end of the line, they may say the reading is actually 5.1 centimeters because their imagination could be different from mine. And yet another person might say that the reading is actually 5.3 centimeters. But no one would say that the reading is 5.0 centimeters because the line has clearly crossed this marking numbered 5. Nor anyone would say that the reading is 5.4 centimeters or 5.5 centimeters because they are far to the right of this end of the line. Such estimates are wrong. So if we take multiple readings of this end of the line, with a high degree of confidence, we can tell they would all be between 5.1 centimeters and 5.3 centimeters. So I cannot tell the exact reading because the value of this digit is estimated. But with a high degree of confidence, I can tell that it is between these two values. So there is some uncertainty or error in this reading, and the amount of uncertainty is plus or minus 0.1 centimeters. 5.2 minus 0.1 is 5.1. 5.2 plus 0.1 is 5.3. So this is the amount of uncertainty or error present in this reading. Similarly, what will be the reading at the other end of the line? We may think that this end of the line has perfectly aligned with this marking numbered 3, but in reality, there will be the same amount of uncertainty in this reading as there is in this reading. So the value of RA would be 3.0 plus or minus 0.1 centimeters. Then the length of the line would be RB minus RA, that would be 5.2 centimeters plus or minus 0.1 centimeter minus 3.0 centimeters plus or minus 0.1 centimeter. Now 5.2 minus 3.0 is 2.2 centimeters. What should we do with these uncertainties? Should we cancel them? No, we should report the maximum possible amount of error or uncertainty. Say the amount of uncertainty in this case is minus 0.1 centimeter. Then in this reading it could be plus 0.1 centimeters. I am looking at the extreme cases. So minus 0.1 minus of plus 0.1 is minus 0.2 centimeters. When the amount of error here is plus 0.1 centimeter, it could be minus 0.1 centimeters here. So plus 0.1 minus of minus 0.1 is plus again. So it would be plus or minus 0.2 centimeters. So this is the length of the line and this is the amount of error or uncertainty in the measured length of this line. So this measurement tells us that the actual length of the line is somewhere between 2.0 centimeters and 2.4 centimeters. 2.2 minus 0.2 is 2.0, 2.2 plus 0.2 is 2.4. So even in this case, what we have here is a range within which the actual value would fall. Then what is the benefit of putting so much of extra effort in estimating the value of this digit? See, in this measurement there are two digits and the value of the first digit is obtained by using the markings physically present on the scale. So we are 100% sure about the value of this digit, but the value of this digit is estimated using our imagination. Because there could be some error in our estimation, we again ended up with a range of uncertainty within which the actual length of the line would fall. Now, what is the benefit of putting so much effort in estimating this digit if we again ended up with a range of uncertainty instead of the actual length of the line? See, when we did not know the value of this digit or this something, the range of uncertainty is between 2 centimeters and 3 centimeters. By putting some effort in estimating the value of this digit, we reduced the range of uncertainty to 2.0 centimeters and 2.4 centimeters. So we narrowed down or shrunk the range of uncertainty by estimating the value of this digit. So this measurement tells the length of the line more exactly than this measurement. Or in other words, this measurement is more precise than this measurement, because here the range of uncertainty is less. We narrowed down the range within which the actual length of the line would fall. So by estimating this digit, we increased the precision of the measurement or exactness of the measurement and reduced the amount of uncertainty or the range of uncertainty. So that is the benefit of estimating the value of one digit in any measurement. So whenever we make a measurement, we must always estimate one digit more than what the measuring device allows us to measure. In this example, the measuring device allows us to measure only one digit, but by using our imagination, we estimated the value of another digit, and that helped us in reducing the amount of uncertainty or increasing the precision of the measurement. So you take any measurement, it contains one estimated digit, and because it is an estimated digit, there is some error or uncertainty in its value. That is why the estimated digit is also known as the doubtful digit. Now comes the interesting part. When we knew the value of only one digit in the length of the line, the amount of uncertainty is 1 centimeter. 3 minus 2 is 1. But when we knew the values of two digits in the length of the line, out of which one is an estimated digit, the amount of uncertainty has reduced to 0.4 centimeters. 2.4 minus 2.0 is 0.4. So with one estimated digit, we could reduce the amount of uncertainty by so much, from 1 centimeter to 0.4 centimeters. Then why can't we estimate more digits in the length of this line and reduce the amount of uncertainty even further? Of course, you can do that, provided you are reasonably confident about the values of those digits. But you can never be sufficiently confident about the values of more than one estimated digit in any measurement. See, we are not even 100% sure about the value of this first estimated digit. Then how confident can we be about the values of these digits? So never estimate more than one digit in any measurement. So a measurement must contain only one estimated digit. And in very rare cases, there can be up to 2 estimated digits, but never more than 2 estimated digits. But in most of the cases, you can have only one estimated digit in a measurement. So that means the estimated digit is the last digit in any measurement, or your measurement must stop at the first digit that has some error or uncertainty. Now the question is, how do we reduce this amount of uncertainty even further, or know the length of this line even more precisely? You may have noticed that as the number of digits in the measurement increase, the amount of uncertainty decreases and the precision of the measurement increases. Here we knew the value of only one digit and the amount of uncertainty is 1 centimeter. Here we know the values of two digits and the amount of uncertainty is only 0.4 centimeters. So obviously, as the number of digits in the measurement increase, the amount of uncertainty reduces and the precision of the measurement increases. So if you want to know the length of this line more precisely, you must discover the values of more digits in its length. But because we are allowed to estimate only one digit in any measurement, the rest of the digits must all come straight out of the measuring device. So if you want to know the length of this line more precisely, you have to pick a measuring device that gives you more digits straight out of it. That is why a measuring device that could discover more digits in a measurement is said to have a higher precision. Now let us look at different measurements for the diameter of this cylinder obtained by using different measuring devices. By using a ruler, we could discover only 2 digits in the diameter, whereas by using a laser interferometer, we could discover as high as 1, 2, 3, 4, 5, 6, 7. 7 digits in the diameter of this cylinder. So as we go from a ruler to a laser interferometer, the number of digits in the measurement are increasing. That is why out of these 4 devices, laser interferometer has the highest precision and the ruler has the lowest precision. And as you know, in every measurement, the last digit is an estimated digit, so there is some uncertainty in the value of that digit. That's why it's called the doubtful digit. And we are 100% certain about the values of all other digits present in the measurement. If there is uncertainty in every measurement, why are we not showing the amount of uncertainty next to the measurement? If we don't show the amount of uncertainty in a measurement, does it mean that there is no uncertainty in that measurement? No, that is not what it means. If the amount of uncertainty is not explicitly shown, then you have to assume the amount of uncertainty in that measurement by using a thumb rule. That is what we call the implicit uncertainty. And the thumb rule says the implicit uncertainty must have a unit value or the number 1 in the same decimal place as the doubtful digit in the measurement. In this measurement, the doubtful digit is in the 10th place. So this is the assumed uncertainty in this measurement because it is not explicitly stated. And in this case, the implicit uncertainty is 0.01 centimeters because here the doubtful digit is in the 100th place. So there must be a 1 in the 100th place of the uncertainty, and the rest of the digits must all be zeros. And in this case, it is plus or minus 0.001 centimeters. And in this case, it is plus or minus 0.12345. 1, 2, 3, 4, 5, and then a 1. So this is the assumed uncertainty in this measurement. So that means as we go from this measurement to this measurement, the amount of uncertainty is reducing. 0.01 is smaller than 0.1, and this is smaller than this, and this is way smaller than this. So the amount of uncertainty is reducing, or in other words, the certainty of the measurement is increasing, or the exactness of the measurement or the precision of the measurement is increasing. And all these digits in the measurement, including the estimated or the doubtful digit, are known as significant figures or significant digits. In this measurement, we are 100% sure about the value of this digit plus one estimated digit. So we have 2 significant figures in this measurement. And in this measurement, we are sure about the values of these 2 digits plus 1 doubtful digit. So we have 3 significant figures. And in this measurement, we are 100% sure about the values of these 3 digits plus 1 estimated digit. So we have 4 significant figures. And in this example, we are 100% sure about the values of these 6 digits plus one estimated or doubtful digit. So together we have 7 significant figures. So as we go from this measurement to this measurement, the number of significant figures are increasing and the range of uncertainty is decreasing, or the precision or the exactness of the measurement is increasing. So significant figures indicate the exactness or the sharpness or the precision of the measurement. The more the number of significant figures, the more the precision of the measurement is. Earlier we discussed about 2 kinds of errors, systematic errors and human errors. Systematic errors are caused by defects in the measuring device. And if you remember this badly numbered scale, every measurement obtained using this scale is bigger than its true value. So we said they are unidirectional. And to obtain the true value, we have to subtract 1 centimeter from the measurement given by this scale. So they can be corrected as well. Then we discussed about a badly calibrated scale. The scale says each division on it is 1 centimeter long, but in reality, each division is much longer than 1 centimeter. So every measurement obtained using this scale is smaller than its true value. And say each division is actually 1.5 centimeters long, then to obtain the true value, we have to multiply the measurement given by this scale with 1.5. So they can also be eliminated and they are also unidirectional. Then we said human errors can also be eliminated. Then we discussed about a third kind of error, or uncertainty. This error or uncertainty is not because of a defect in the measuring device. This is because we are trying to estimate the value of 1 digit more than what the markings on the measuring device allow us to read. And because this is an estimated value, there could always be some error or uncertainty in it. That is responsible for this error or uncertainty. The value of this estimated digit could sometimes be more than what it should be and sometimes be less than what it should be. We cannot say that every time the estimated value is bigger than what it should be or smaller than what it should be. That means these errors are not unidirectional. So if you measure the diameter of this cylinder using laser interferometer multiple times, sometimes the measurement obtained may be slightly smaller than the actual diameter, or sometimes it may be slightly more than the actual diameter. So these are not unidirectional, and because we cannot tell whether the next measurement will give a smaller value or a bigger value than what it should be, they are called random errors. And random errors cannot be eliminated because they are due to this estimated digit. So in every measurement, there will be some amount of random error that cannot be eliminated. But we can reduce the amount of random error by measuring with an instrument with higher precision. That is an instrument that gives more digits in the measurement. That's what we did here. This is the diameter of the cylinder measured by using a simple ruler, whereas this is the diameter of the same cylinder measured by a laser interferometer. And here the amount of implicit or assumed uncertainty is plus or minus 0.1 centimeter. Here it is plus or minus 0.01 centimeter, plus or minus 0.001 centimeter here, plus or minus 0.000001 centimeter in this case. So as we go from this measurement to this measurement, as the number of significant figures increase, the amount of random error decreases, or the exactness or the precision of the measurement increases. But even in this measurement, there is some amount of uncertainty, even though it is very small. So even this measurement is not 100% precise or exact. But when will a measurement become 100% exact? When the amount of uncertainty becomes exactly 0, that is 0.0000 up to an infinite number of zeros. But when will the amount of uncertainty become exactly 0? When you measure something up to an infinite number of decimal places with absolute certainty. But is it possible to practically measure anything up to an infinite number of decimal places? No. That is why there will always be some amount of uncertainty in any measurement. So that is why all measured values are inexact values. Because every measurement contains some amount of random error or uncertainty. So that means it is impossible to measure the exact diameter of this cylinder, or the exact mass of an object, or the exact temperature of a fluid, because these are all measured quantities, and every measured quantity has some amount of uncertainty. Then do we know the exact value of anything without any doubt or uncertainty? Of course. When I say the number of students in a classroom is 14, I mean it is exactly 14 without any doubt. That is why sometimes I can write it as 14 with an infinite number of zeros in the decimal part. Similarly, the number of fruits in a basket, the number of books in your bag are all exact values. That is, values that you obtain by counting are all exact. Similarly, values that are assigned by definition are also exact values. By definition, 1 dozen is a group of exactly 12 items. We defined it that way. We said so. That is why we sometimes write 1 dozen as 12 with an infinite number of zeros in the decimal part to indicate that its value is exact. Similarly, 1 foot is exactly 12 inches by definition. So sometimes we can write this as 12 with an infinite number of zeros in the decimal part. Similarly, the freezing point of water is 0 degrees centigrade exactly, and the boiling point of water is 100 degrees centigrade exactly. So values that are assigned by definition, values obtained by counting are exact values. That is, their precision is 100%. But values obtained by measurement are inexact values because of this uncertainty or doubt. So whenever you measure something, you always get a range of uncertainty, but not the exact value. And here comes the last part of this video. This is the diameter of the cylinder measured by using a laser interferometer, and it has 7 significant figures, and this is the estimated digit or the last digit, and no digits are shown after this last digit. That does not mean that this is the last digit in the diameter of the cylinder and there will be nothing after this digit. This only means that this is all a laser interferometer could do. That is, it could measure the diameter of the cylinder only up to 7 significant figures. And if you want to know the diameter to even more significant figures or even more precisely, you have to use a device with even higher precision or invent one for yourself. So, in this measurement obtained by using a laser interferometer, we know the values of these 6 digits with 100% certainty. And this is the estimated digit or the doubtful digit, and we know nothing about the values of the remaining digits in the diameter of the cylinder. That is what this measurement means. So we do not know the value of this digit. It could be a 1, it could be a 5, or it could be any other digit. We have to figure out the value of this digit by using a more precise measuring device. But because we do not know its value just yet, can we assume that its value is 0? Or can I say the diameter of the cylinder is 1.5928470 centimeters? That is, can I add one trailing 0 to this measurement? Because mathematically these two values have the same magnitude. You know, you can add any number of trailing zeros to the decimal part of a number without changing its value. You can do that in case of exact numbers, but you cannot do that for measurements, because in every measurement the last digit is the estimated digit or the doubtful digit. So if you add a trailing 0, then the reader would think that this is the doubtful digit and the values of all other digits are known with 100% certainty. But that is not the case. Actually, this 7 is the doubtful digit. So by adding this trailing 0, we are incorrectly shifting the uncertainty from this digit to this digit. Thereby, we are increasing the precision of the measurement, because if you go by this measurement, the amount of uncertainty would be plus or minus 1, 2, 3, 4, 5, 6. So 0.123456 and a 1 centimeter. Obviously, this is smaller than this. So by adding this trailing 0, we have reduced the amount of uncertainty and thereby increased the precision of the measurement. So you are telling the reader that your measurement is more precise than what it actually is by adding this trailing 0 that is not originally there. That is why you should not add trailing zeros to the decimal part of a measurement. Doing that would increase the precision of the measurement incorrectly. Okay, then what about dropping trailing zeros from the decimal part of a measurement? Say we measured the mass of an object and found it to be 13.600 grams. These two trailing zeros in the decimal part have come out of the measurement process. I did not add them. We put effort to know the values of these two digits and found them to be zeros. They could have been any other numbers instead of zeros. So in this measurement, this is the estimated or the doubtful digit. So the implicit or the assumed uncertainty in this case is plus or minus 0.001 grams. And if you choose to drop these two trailing zeros, then the measurement becomes 13.6 grams. Then this digit becomes the doubtful digit and the assumed uncertainty will become 0.1 grams. So if you choose to drop these two zeros, then the amount of uncertainty would increase. This is much bigger than this. Or the precision of the measurement decreases. So you put effort to figure out the values of these two digits, then why do you waste your effort and drop them and reduce the precision of the measurement? That does not make sense. So we should not add trailing zeros to the decimal part of a measurement if they are not part of the original measurement. And it does not make sense to drop trailing zeros from the decimal part of a measurement if they came out of the measurement process. Doing that would reduce the precision of the measurement and waste your effort. So in this video, we discussed about systematic errors, human errors, random errors, and a little bit about significant figures.